can start. Our today's subject is discrete time Fourier transform. It's long name. What is it? Let's start with idea. I have a periodic signal. It's something periodic. Plus m, where m is an integer and t is a real number, repetition period. So signal repeats with a period, t capital. I would like to perform Fourier transform on it. To get its representation as Fourier series. But 1 second, I will write. So I will need to calculate cosine as 2 divided by time 0 cosine double p time and sine 2 divided from 0 to time my signal sine a double p. It's simple. Here are my factors for Fourier rule. Now, let's look on case. I do not operate with continuous signal, but I do my job with signal in form of table. Signal is in discrete time. For simplicity, I will start from C1. It will be 2 divided by time, and from 0 to time. Signal, cosine, simple, 1. Time, signal of time multiplied by cosine. I don't know, maybe something like this within one period. White line is signal multiplied by cosine, but I started with what? My signal is in discrete time. I don't have full values of signal. I have table of values of my disposal. Value measure 1, measure 3. True name for them are samples. These are samples. So I have set of samples, starting from the first one, and it's a number of samples within one period of time. I can calculate signal multiplied by cosine only in where signal is measured. My signal is represented by table of values. I can tell anything about signal only when it's measured. So only for elements of this table. Multiplying unknown signal with known cosinus, result will be unknown. So there is nothing between sampling points. I need to calculate this integral to obtain Fourier factor. Physical meaning of this signal. of this integral is an area of white figure. But I can't calculate it exactly because I don't know signal. What I can do, I can connect something like this, in this way. And I can say what approximately area of white line, white figure, white area is equal to sum of these rectangular areas. Area of one rectangle is h multiplied by a, or signal value at point I, yeah, multiplied by value of cosine at, and here is one tricky moment. I started numbering 1, 2, 3, 4. Value angle for cosine at this point is 0. Meaning, I have a shift. I can start numbering from 0. This means what last point will be n minus 1. I started from 1, it's natural. But I need to take into account what angle here at this point is 0. That's why I need to write I minus 1 multiplied by what's the space of one rectangle of one step? Double P divided by number of steps. Full period for cosine is double P. Here, double P, period. When time is equal to period, I got 1, so it's double P. Each step is double P divided by number of steps. It's multiplied by period divided by number of steps. If we speak about time, this distance, because this point is a full period, dividing by n. Now, I can write full area of C1 will be double divided by time, multiplied by time divided by n, multiplied by sum of all rectangles. It will be value of signal multiplied by cosine I minus 1 double P divided by n. Here I got numerical factor for cosine of the base frequency. What will be, I would say, travel or speed of maybe speed of rotation for cosine for second harmonics? Here will appear 2. For third will be 3. And so on. Meaning what I can write. Factor number k for cosine 2 divided by n. Somewhere I starts from 1 and ends to n. Signal values multiplied by cosine of I minus 1 k double P divided by n. Same way I can write, I need sine somewhere I starts from 1 to number of point, signal values sine I minus 1 k double t divided by number of point. Here I got very easy two formulas for discrete time Fourier transform. It's simple way. They are optimized version. They are hiding I under name FFT, fast Fourier transform. They all first they rely on sine and cosine symmetrics, and second they are models harvesting on processor architecture. But there is one important moment. All fast Fourier transform versions require n being power of 2 or symmetry not work. Be careful. Check if you use some ready-made algorithm. Check what it's do if number of point isn't power of 2. Some fall back to this form, to classical discrete time Fourier transform. Some do zero padding. They substitute missing point with zeros. Zero padding is a rubbish. Problem with in power engineering business, we do not need full row, it's one. And second, usually in our application, this, how to say, we often use time steps, sampling time, producing this sampling series, not power of 2. Very typical for our business use, for example, 1 millisecond. This meaning 20 measurements per period. 20 isn't power of 2. Because we don't need full row, we are not obliged to use fast transforms. And we use traditional discrete time Fourier transform. Okay, why I'm writing this? One more transform, blah, blah, blah. This is very useful tool when you need to perform network analysis for non-harmonic currents. Very good example I have on my table is a rectifier powered network. I have AC source and draw it this way. Here's something. Rectifier powered network. Can I get rectifier voltage? It is. Okay. Here you see true output voltage of rectifier. Is it AC? No. Is it DC? No. This voltage is outside of simple electrotechnics theory. How can I perform network calculus for such voltage? My network is powered from rectifier. What should I do? One of the way to get this network analyzed, I need a stable regime. At first, don't bother about transient. How can I get stable regime of such network? Stable mode. What question? Okay, what can I do? I can take my signal and write it in the form of samples table or table of values. I thought 1, 2, 3. Something involves blah blah blah. I can perform sampling. I can write signal in form of table. Then I can apply discrete time Fourier transform. What will I get? C0, which is DC component, C1 S1 will be AC source for 1 omega t for base frequency. C2 S2 AC source for double omega, C3 S3 for triple omega, and so on. After I apply discrete time Fourier transform, I will get one DC component and multiple AC components. Next, I have my circuit, capacitors, coils. I will apply first C1 S1, I don't know, CM SM to my circuit one by one. This means what mean applying? These components are ideal AC. Yeah? I can perform network analysis by the rules of classical electrotechnics theory. It's clear. So I will get voltages, AC voltages, starting from 1 and ending by M. I will have branch current. It's in Latvian Saks, it's a branch in Latvian. I will have a set of branch current for each frequency. Here, after discrete time Fourier transform, I have range of frequencies. Starting from base and ending at Nyquist frequency, I can go, there is one law in all discrete transform. Sampling frequency should be at last twice higher than maximum frequency of my signal. It's a rule of Nyquist. So I will have, in theory, I can have my harmonics up to Nyquist frequency, so half of sampling rate. One more. I also need to perform analyze for DC. It will be M plus 1 regime. I result, I should get number of AC harmonics, AC circuit solved, plus one circuit for DC mode. It will actually it's number 0. What then? What my result is Fourier factors. Apply inverse Fourier transform and you will get nothing else than true voltages and currents. Let's try to see it. First I need voltmeter. I would like to know voltage. Where is my voltmeter? I forgot to take batteries. .53. 20.53 is effective value of supply voltage. And now where is my everything works, don't. Where should I go? Where should I go? Here's my example. One moment. I need to switch for my online viewers. Again, something not working well. Oh, now it's okay. Now it's fine. Now it's fine. Now it's fine. Come here. You come here. I need this wire. It's not a simple wire, it's a cable. Here is space to write something. Clear. I will use CELAP environment because it's free. And it has all mass I needed. I can do one thing. I can copy this from myself, but this is not needed. This what I will need, and no, here this is wrong. 20.5 also I don't need this. And one more part is missing. Yeah, I would like to get this from myself previous. What I wrote, come on. I will have 720 points in my table. I will do it in step 1/2 of degree. Then my voltage, I measure it, it's 20.5 volts. I'm filling values of omega time. It's for drawing a chart. I will need it. But here, values of my signal. Rectifier, absolute value. Absolute value of sine. Why I have here square root of 2? Because I measured, got measured effective value. Okay, let's see how it works. I should get table of values. Drawing it with plot, I should see something close to what we saw in reality. Here it is. Oops. Something familiar? Yeah, voltage we saw. Now, next step. I have this nice voltage. My next step, I need to perform Fourier transform. I will copy this part from previous me. What's going on here? I will take 50 harmonics. For each harmonic, I need to calculate. Oh, I have erased. Here are my sums from my nice theory, my numeric integration sums. Again, for cosine 2 divided by number of measurements, sum where I start from 1 and ends at number of measurements, values of signal multiplied by cosine of I minus 1 multiplied by k double p divided by period. For sine, that's right, sk 2 divided by n, sum I starting from 1 the number of point, values of signal, sine I minus 1, k double p divided by number of points. Here are the sums, k double p divided by n, 2 divided by n, and here for this one is for DC component. If I do didn't make mistake, result will be 50 cosine factors, 50 sine factors, plus 1 DC. How can I check result? Perform a Fourier transform and compare it to original signal. So here is in Fourier synthesis, and I draw together my signal and result of synthesis. If lines overlap, it's okay. If not, I made something wrong. Let's try to see it. Here is table of my signal, and here is my result. What's going on online? Yes, I think fine. Here is my result. I can enlarge it. There is a difference, of course, because Fourier will not, this sharp change, interruption, will not be ideally reflected by Fourier law. But you can see no disasters here. Yeah, I'm making some error. So this is synthesis. Here, blue line, inversion of Fourier transform. It's what blue line is what my Fourier law represents. Green line, true voltage. Fine. I think I can live with this. Here is my. Now I have what? Sorry. Cosine values. 50 Hertz, 100, 150, 200, and so on. Here are cosine values, AC. My DC component, and no sine, because I start from 0. Okay, I can work with this. Now I need to perform network solutions. I need to do it automatically. I will not do it by hand. How can I perform? Where am I? So now I need to do network solution. First I need to draw my network. What will I solve? I need my network. Perform network analysis. For this. Okay, what do I have? Coil 10 millihenries, and its active resistance 6.44 ohm. My rectifier now is a signal here. 10 millihenry, 6.44 ohms. Here will be ground. This coil. Next, down is going capacitor, 10 microfarads. Next element, this nice coil. It's a standard neutral inductance. 100 millihenry. So it has self-inductance, self-resistance, neutral. I used added one resistance to prevent overheating. This one is 220 ohms. Data for my coil. Primary 17.5 ohm and 82.77 millihenry. Self 82.77 and 17.5 ohms. On secondary side, they are coupled with 100 millihenry metal inductance. Secondary side has all inductance, all resistance. Called self 35.9 and 234. Self of secondary winding. Next, this resistance box is set to 600 ohms. And I have added 10 millihenry inductance. Yeah, this one is grounded. Here is my network. If someone, 1 second, I will show it. Here is my network. If someone asks you to perform manual analysis of such network, kill him. Metal inductance. Okay. This network is not for hand solution. It can be solved by hand, but with the what's this? We call it clock. So how can I perform analysis of such network? I will do it with the help of topological analysis. I will not do it by hand. First, I need to select base node. Here, when my scope is attached, this will be my base node. When I have base node, I need to mark other nodes and assign them numbers. Node will be any point where I can attach my scope, where I can get voltage. More. I can here maybe use them as a one branch. Okay, they can be one branch. Here I apply those. Here is my node numbers. I need to assign numbers to all nodes except base node. Next step, branch. I need to assign numbers to my branch, and that's not all. I will need to set directions. Okay, this will number 4, and this can be number 5. Here I did a preparation work. No, not enough. This one will be number 6. Oh, yes, now it's good. I have assigned numbers to all my branches. Now I need to convert. First, I need to somehow specify network topology for my computer. This is done with its special matrix called first incidence matrix, conduction rule, branch, node. Row numbers are node numbers, column numbers are branch numbers. If branch inflows in node, I should write -1. If it goes from node, I write 1. M, the first matrix of incidence. No, if not connection, I will write 0. For my network, one, two, three node. 1, 2, 3. 1, 2, 3, 4, 5, 6. First matrix of incidence. First node, what we see? First branch inflows in first node. This means what I'm writing -1. No more connection. Branch number 2, outflows from first node. 1, 0, 0. Branch number 3, 1, 2. 1, 2. Correct? Correct. Branch number 4, 3 to base. This is base node. 1, 0, 0. Branch number 5, from base to 3. -1, 0, 0. And number 6, from second to base. 1, 0, 0. Now I need to put it into my program. Where is my program? Where is my where is my near genius program? Can I steal something from here? Oh, I can steal the size. I can steal this part. I only need to erase this one and write my own. It will be -1, 1, 1, 1, 0, 2, 0, 3 zeros. Second row 2 zeros, 0, 0, -1, 0, 0, 1. And third row 3 zeros, 1, 2, 3, 1, -1, 0. One moment, I will get 145. Who are you and why are you here? I will make it look better. Square bracket. Yes, I don't need this. I don't need this. Save. Errors. No errors. Okay, I can live with this. Here is my network topology, and I copied frequency 50 Hz. It's okay. What about these two rows? Size is a measuring operator. It accepts two arguments: what to measure and how, or number of dimensions. 1 means get number of row. 2 means get number of columns. Here, ZS, it's from Latvian Zara skaits, number of branches. MS, Latvian mezglu skaits, or number of nodes. I will need transposed M. I need to, you know what I mean, transpose matrix? When number of row swaps with number of column. Here is transpose of M. I did it with a very simple pair of cycles. What my schematics is missing? I don't have resistance. I have topology, connections, branch nodes, but I don't have any resistance. This should be done with the help of resistance matrix. Resistance matrix forms in a special, say, law. Its diagonal are complex resistance of branches. So it's matrix branch number. Resistance complex of first, second number of branches. A diagonal own or self resistance. Other elements are mutual. If between, I don't know, branches K and L are coupled with mutual inductance, KL will be equal to AK and equal to omega M. For self, I need space. For self, for resistance, we write resistance. For coil, omega L. The complex resistance. For capacitance, 1 divided by omega C. As per classic electrotechnics. In my case, where am I? Yeah, I'm here. Let's take this part, but I will need to modify it. What's here? See? Cycle from 1 to number of harmonics. I will need to perform my calculus for any AC regime, for any AC harmonic. At this moment, I have 50 of them, yeah? Yeah. So for each one, I will need to perform network solution. Here, complex, it's create a complex number from 0. What's this? K double P multiplied by F. Double P multiplied by F is an omega, is an angular frequency. K number of harmonic. For base, for 50 Hz, 200 Hz. For each one, this one needs to be revoked. This one is not fine. Let's see what we have at first branch. 1 second. Maybe I will not destroy it instantly. Look what I have. First branch is okay. 10 millihenries, same coil. Second branch, 10 microfarads is okay. 17.5 plus 8277 also okay. 220 is number 220 not okay. 220 not okay. Number 4. Number 4 is a self. Yeah, because in my previous lecture I used the same metal inductance. These are okay. This one needs to go. Branch 5 is 600 plus J omega multiplied by 10 millihenries. Or here 10 millihenries, and the sixth one is 220 ohms. Now this part I have created. This small is a main diagonal of resistance matrix. Own or self resistance, inductance, capacitance of my branches. I have created, this is near complete resistance matrix, except one I need to put metal inductance. Branches 3 and 4 are coupled with metal inductance of 100 millihenries. These are metal. Now, some function. I will need 1 second. I need to inverse resistance matrix. 1 second. I will copy from myself. Jordan. It's a function of matrix inversion, so-called Jordan exclusion. I need to put it in my code. It's simple, performs matrix inversion. So here, boom. Fine, I will get inverse matrix. Look at this. EMF, vector of EMF, I need to put EMF somewhere. I will use vector for a branch. Here I have in my network, I have only one EMF. It's my rectifier substituted with Fourier series. So EMF is an element of my Fourier composition. I'm solving very simple by inversion, through inversion of nodal admittance matrix. What I'm solving? What's here? I can solve my network by solution of nodal voltage equation. This equation is my nodal voltage equation. It's a derivative from the nodal potential technique, where this matrix called nodal admittance matrix. It's M inverse, M transposed. That's why I needed M transposed and inversion of resistance matrix. This one will give me nodal voltages. Current, if I would have current sources, this is for current sources. I don't have current sources here. In theory, when needed, you can use this element with controlled current source. But this I need. It's incidence, resistance, vector of EMF. I used only, since I have only one EMF in first branch, I fill this vector with, here, I filled it with 0 and add complex value of my harmonic, or phasor of my harmonic. Since I perform this for all AC harmonics, I will solve 50 regimes. Voltages, branch currents through the Ohm's law. Results will be stored in U matrix, where what will happen? Each column will represent one frequency. Not own, but one frequency. As a result, I will get matrix with 50 columns, 50 voltages, and 50 branch current. This is good, but not enough. I need to solve DC. And here, if I would follow good practice, what should I do to solve DC? I will need to create DC schematics. Exclude all capacitors, because capacitor resistance is infinite in DC mode, and short circuit all coils, because inductance is 0 at DC. I will need to create schematics, and one more object, I need to create a table of correspondence. Which branch in AC network corresponds to each branch in DC, because part of branch will go away. I'm lazy. I will do a trick. 1 second, I will copy my trick. See what I'm doing? I will solve DC mode as a very slow AC. It's not right by strong theory. It will assault purists, but I will do because it's my program. I do what I want. I will, to save myself time, I'm simply solving DC mode as a very slow AC. 1 milliradian per second. Okay, I will get, see where I'm solving, n harmonic plus 1. 51, column number 51 will be DC mode. Next step, what I need to do? Actually, I have now my solution, but in form of Fourier series. I need to perform inverse transform. Synthesis for voltages and synthesis for current. Very simple. I just perform synthesis of Fourier law. Now let's see what will happen. Maybe, wait 1 second, I will kill this, run. Oh, anyway, it's a number 2. Here are my voltages. Oh. Here are my voltages in theory. Let's do something. Voltages. Oh. Voltages for people working online. Here, my voltages. Voltage. Magnitude at point something like 29 volts. Peak something at 29 volts. Okay, voltages. Where is my another one? The capacitor. Come here, my dear school. Another one is at capacitor. Calculate. Up, kind of step, one more step up. Yeah. Sorry. Up, kind of step, one more step up. Maybe I need more harmonics. Second. Let's make it a bit more precise. A bit more precise. I will add 70 harmonics. Yeah, run. The step is bit different. Hey you. If here I have pause, 1 second. Hey. Oh no. It was stupid, I got everything inverted. Sorry. This experiment isn't needed. definitely. In opposite. One started. Go. Fine. No. There. There is a big difference. I don't know why. Let's take a look on voltage at node 3. Voltage at node 3 is a very character. Here. Oh, see, voltage at node 3, 5 volts. It's a very characteristic peak. Node 3 is where 600 ohms resistance is attached. Here is my true voltage at node 3. I can switch. Yeah. Here is my true voltage at node 3. And numeric solid voltage at node 3. Up, down, AC, approximately 5 volts. Here. Two volts, 4 volts. Yeah, here it is. I can try to get currents. 1 second, I will get current sensor. That's how current should look like. I need a second, really. Current sensor. is current in a branch 1. 1, 2 oscillates. 1, 2 decay. This one. Current in branch 2. 1. Current in branch 2. Current in a branch 2, real. It is it? Is it? Branch 4. From this one. No, it's below. Sensor. Signal too small for the sensor. Yeah, oh. Wait. Валить, тут нам пошло maybe, branch 6. Great color. I'm below sensor. Branch 6, branch 6, branch 6, branch 6. Like this. Current in branch 6. Current in branch 6, and where is my this one. Blue line, current in branch 6. Yeah. Appears I solved network correctly. Yeah. Okay, network. I can switch off. Here, with the help of discrete time Fourier transform, I can solve very complex network. I just need to what the process? Create signal table, perform discrete time Fourier transform, solve multiple ideal networks, perform Fourier synthesis, and you got everything. All values you may need. Fine. Now what I need to do? Come here. I need to import. Come on, you. Oh, fine. This is nice. 0 viewers online. Ah, come on. Yeah, here it is. Appears fine. Okay. Any questions? Very easy. Can I add blah blah blah, all kind of demon. Yeah, I'm in. Oh. I don't know how good it's. 1 second, I will edit it. This one will go to hell. I will simple. Come on. Where are all my this one is sour. This one what we created today. Here it is, the FT application. You can always get it. Is a code I wrote today. But no, maybe. What day we have? 19/02/226. Oh. Fine. It's at the end of. Who are these people? Why they are looking at me? Yes. So it's a very powerful tool, real discrete time Fourier transform, when you need to perform complex network analysis. Only one moment. It's applicable only for periodic. You can't use it for transients. Okay. This is not needed. Can take a break. We have one more lecture today. I will speak on errors of Fourier transform. Online, no.